Good morning, ladies and gentlemen. I am Longkun.
I'm Wenjie.
We are happy here to present our works.
This is a work joint with Professor Chenchen, Dachuan, Dingzhu.
In our problem, a sink emits mobile sensors for coverage. Sensors can be UAV, drones, robots, vehicles, and so on. We will first introduce the problem. We are given a set of sinks distributed on the plane. Sink Si is with position xi, yi, and can emit infinite many sensors.
Here is the barrier for coverage. The aim is to completely cover the barrier by sensors for things with minimum total movement.
Here is a solution to the instance. Note that we don't use sink S2 because it's too far away from the barrier.
Here is the formal definition of MinSum SLBC.
This is an example of MinSum SLTC, which covers the target on the line barrier instead of the barrier itself.
There is the previous result for covering targets on the plane. It's NP hard but admits p-task.
One in-sensor version of the problem, that each sink contains exactly one sensor, we have both computational and algorithmic results. One sensor version of the problem, that in 1D setting that sensors initially on the line containing the barrier, the problem is non-polynomial solvable.
In 2D setting, sensors initially on the plane. We don't know if the problem is NP hard. Still, there are approximation algorithms.
As our main result, we reveal that non-uniform SLBC is NP hard. In non-uniform SLTC, the discrete version is polynomial solvable by design algorithms.
We show that the decision non-uniform SLBC is NP-complete by reducing from the partition problem.
In an instance of partition, we are given a set of positive integers u, and the aim is to determine whether u can be partitioned into two subsets such that the sum of both subsets are equal. And we want to show that an instance of partition is feasible if and only if the corresponding instance of our problem is also feasible.
A natural idea of the transformation is to use the integers of partition as sensor ready.
But there are problems. First, how to relate ready and movement of the sensors. As you see, we can only set the bound for total movement. Second, each sink can emit many sensors, but an integer of partition has only one copy.
So we try again. First, we want to relate ready with movement.
So we let the movement of a sensor roughly linearly dependent on its radius.
Second, we want to make sure each sink can emit at most one sensor. We construct two sinks for each integer.
The trick is the difference between the radius of the two sinks is ui. So one sink corresponds for using the integer and the other sink is for otherwise.
Then we set barrier. Here val k is the number of integers or pairs of sinks, and n the sum of the numbers in U.
Lastly, we place sink I at the position on the vertical bisector of the barrier, but very far away from the barrier. We observe in such a position far away from the barrier, the movement of covering any point of the barrier by sensors from the sink is roughly the same.
Here is an example of the transformation.
We showed firstly that if the radius sum of used sensors is exactly half L, then the movement sum must be bounded by this number. If the radius sum of used sensors is at least half L plus 1, then the movement sum must be strictly less than this number.
That is, a sum of the radii of the used sensor in an invisible solution must be exactly half of L.
We then showed each pair of things must contribute exactly one sensor to the coverage.
By the two property, we eventually obtain the correctness of the reduction.
Here we shall give our algorithm for uniform SLTC. We cluster the targets into groups and then model the groups as vertex to consequently construct an auxiliary graph.
A target group is a set of targets that can be covered by a sensor.
For example, here target 4 cannot be a group because any sensor covers either 3, 4 or 4, 5, but not 4 alone.
Here is the construction of the auxiliary graph that accommodates the transformation.
The group C1 contains the leftmost target, so we add an edge between the source node S and C1. And here is the second node. Here's the third group, and here's the fourth group. The group C1 and C4 has no gap, so there's an edge between C1 and C4, also an edge between group C2 and C4. And here's the fifth group, and here's follow-up ones. Here are group 11 that contains the rightmost target, so we add an edge between C11 and destination node T. This completes the construction.
We prove uniform SLTC can be optimally solved in O(n)² runtime.
The key idea of extending to non-uniform SLTC is computing a set of groups for each distinct radius and combine the groups as one to construct the auxiliary graph.
We further extend the math to the continuous version and get an approximation algorithm for non-uniform SLTC.
In the experiments, we compare our algorithm with other baselines. Our algorithm is as fast as the greedy algorithm, but can always produce optimal solution, while the greedy algorithm cannot. In particular, for non-uniform SLBC, our algorithm consumes 30% less moment than the greedy algorithm, but has a comparable runtime. Thank you for attention.